Have you ever imagined just walking through a solid wall? I mean, it sounds like something straight out of science fiction, right? Well, what if I told you that on the unbelievably tiny scales of the quantum world, particles do this all the time? They literally slip through barriers that should be impossible to cross. This is one of the weirdest and honestly one of the most important consequences of the wave nature of matter. So let's dive in and pull back the curtain on this bizarre and fascinating piece of our reality. Okay, so to really get how strange this is, we first have to talk about why it seems so, well, so impossible. We've got to start with the rules of the world we see and touch every day, the world of classical physics. So let's just ask the obvious question. Can you walk through a wall? Of course not. You'd bounce right off. Your body just doesn't have anywhere near enough energy to break through the bonds holding that wall together. It's a simple, non-negotiable rule of our world. Now, in physics, we formalize this idea with something called a potential energy barrier. And this diagram, it shows the classical rule perfectly. A particle's energy, that's the dotted line E, is way lower than the peak of the barrier V0. It's just like a ball trying to roll up a hill that's too steep. It doesn't have the juice. It's going to roll right back down, every single time. It simply cannot get to the other side. And really, according to all our everyday intuition, that should be it. Story's over. The particle gets turned away 100% of the time. But that intuition, the very foundation of our experience, it just completely shatters when we zoom all the way down to the world of atoms and electrons. Because down there, the story is just getting started. So how in the world does the impossible happen? Well, the secret isn't about using more force. It's about completely rethinking what a particle even is. This whole phenomenon has an incredible name, quantum tunneling. That's the official term for a particle showing up on the other side of a barrier that it never had the energy to go over. It doesn't smash through it, it just sort of appears on the other side. And here is the absolute key to the whole thing. Tiny particles, like electrons, aren't just little solid dots. They have a wave-like nature. Their very existence is more like a smeared-out cloud of possibility than a single fixed location. And the rulebook for this wavy behavior, the mathematical key that unlocks this entire mystery, is the famous Schrödinger equation. So the Schrödinger equation gives us what's called the particle's wave function. The best way to think about a wave function is as a probability map. It doesn't tell you exactly where the particle is. Instead, it tells you where it could be. The bigger the wave is at any given spot, the higher the chance you'll find the particle right there if you go looking for it. And this is where the magic happens. When that probability wave hits a barrier, it doesn't just slam to a halt and disappear. A part of the wave actually leaks into the barrier. Now it gets much, much smaller, fading away really fast. But, and this is the kicker, if the barrier is thin enough, a tiny little piece of that wave can pop out on the other side. And a non-zero wave means a non-zero chance of finding the particle there. It has tunneled through. Really, this is the heart of it all. Tunneling isn't some extra weird trick that particles do. It is a direct, unavoidable result of matter behaving like a wave. As soon as you accept that fundamental truth, tunneling isn't just possible, it's basically guaranteed to happen. Okay, I know this might sound like some strange theoretical glitch, but it turns out the universe fundamentally relies on this. This isn't just happening in a lab somewhere. It's a core process of nature itself. You know, for a long time, physicists had a huge puzzle on their hands, alpha decay. You had these heavy atomic nuclei that were spitting out smaller particles. But according to classical physics, those particles just didn't have the energy to break out of the nucleus. The math just didn't work. Then, in 1928, a physicist named George Gamow totally cracked the case. He realized the alpha particle is basically a prisoner, trapped inside the nucleus by the incredibly strong nuclear force. Classically, that's a life sentence. It should be stuck there forever. But quantum mechanically, its wave function can leak right through that nuclear wall. So with every passing moment, there's a tiny, tiny probability it will escape. Over time, that tiny chance becomes a certainty. The particle tunnels out, and boom, the atom decays. So nature uses tunneling to literally transform elements. But we haven't just sat back and observed this quantum weirdness. We've actually learned how to control it and build one of the most powerful scientific tools ever created. Everybody, meet the Scanning Tunneling Microscope, or STM for short. This amazing device's entire operation depends on controlling a steady stream of electrons as they tunnel across a gap that, by all classical accounts, should be impossible to cross. So here's the breakdown of how it sees. You take this incredibly sharp needle, we're talking just one atom at its very tip, and you bring it super, super close to a surface. That tiny gap of vacuum between the tip and the surface, that's your energy barrier. Then you apply a little voltage, which encourages electrons to tunnel across that gap, creating a tiny, measurable electric current. Now, this tunneling current is unbelievably sensitive to distance. So by scanning the tip across the surface and using a computer to keep that current perfectly constant, you can map out the atomic landscape with breathtaking precision. And the results? They're just stunning. This isn't a computer simulation. This is a real image of the individual atoms on the surface of a material. This invention, which was developed back in the early 1980s, was so revolutionary, it won its creators, Binnig and Rohr, the Nobel Prize in Physics. It literally gave humanity its first real look at the world of atoms. So what's the big takeaway here? What's the big picture? Quantum tunneling isn't some obscure little footnote in a physics textbook. No way. It is woven right into the fabric of our universe, from the very heart of atoms to the cutting edge of our technology. When it comes right down to it, tunneling matters because it forces us to accept this wild new reality. Particles are fundamentally waves of probability. It's the engine behind natural processes like radioactive decay, which, by the way, helps keep the Earth's core warm. We've harnessed it to build incredible technology like the STM, and it's become a true cornerstone of how we understand the way everything works. From particles escaping an atomic prison to microscopes that can literally see atoms, quantum tunneling shows us a universe that is far stranger and way more connected than we ever could have imagined. It really makes you wonder, doesn't it? If solid walls are actually leaky at the quantum level, what other things that we think of as impossible are just waiting to be discovered?